Hello class. In lesson and topic 2.9 logarithmic expressions, you will learn the key features of the log functions, including the domain and range, translations, and end behaviors. Okay. Now, let's start with what the definition of a log function is. What specifically is a log function? Well, for values of x greater than 0, so positive numbers, and b, a base that's greater than 0 but not equal to 1, the equation y, make it a little bit thicker. Okay. Let's do the same thing with all of these. 5, okay. All right. The equation y equals to the log with base b of x, okay, this right here is a log, it's equal to this base b raised to the power of y equals to x. This is a log functions. Now, in anything in mathematics, again, everything has to have an inverse operation. So there has to be an operation that can undo, that has to have an inverse, again, to our exponential function. Since this is a one-to-one function, exponential functions always increase or always decrease. There has to be an inverse for this operation here. And that is this operation here, the log function, okay? Kind of weird that we're using words, but we've started using letters and words a long time ago in this in pre-calculus and in algebra as well. So we have this operation here, the log of with base b. That's how we read this, log with base b of x. That is our log function. And the function f of x equals log base b of x is the log function with base b. Okay, so moving on. Now, while our base, this b here, again, could be any positive number as long as it's not equal to 0. There are two special and unique bases that are commonly used. First one, with no pun intended, is referred to as the common log. The common logarithmic function is a log function that has a base of 10. When our base is 10, which is written like this, log base 10 of x, we only write the log parts. So for the common log, this 10 is not written. For any other log, for any other base 2, base 3, base 4, we have to indicate the base. But for the common log, we do not indicate the base. And as a result, again, because this is the common log, that base is understood to be 10 in those situations. The other one is the natural log. The natural logarithmic function is the log function with base e, Euler's number, which again is the approximated value of 2.71. So e, which again is the constant, that's approximately 2.71. In that situation, when the base is e, the notation for that is to use the abbreviation for natural log, L for log and for natural, but is written backwards, of x, okay? So this notation refers that the base is going to be e, and this notation refers that the base is going to be 10. Now, the big idea here is that just like with numbers, how we can write a number from decimal form to a fraction form, we can also write equations from logarithmic form to exponential form or vice versa. These forms create equivalent statements that represent the same claim. We are not changing the problem when we convert back and forth. All we're doing is rewriting the equation into an equivalent form. So for example here, in order to rewrite this from log function to exponential function, we're going to use the definition that a log is equivalent to this exponential form right here on the right, okay? So the way that we do this to convert the following equations from exponential to log, I'm sorry, this is backwards, from log to exponentials. I need to fix this. This should say from logs to exponential, that direction right there. We start by doing this. We start with the base. So here our base is 2. 2 is going to be raised to the power, 5. The base is 5. I highlighted 5. I don't know what I'm saying here. Let me start over, okay? This right here got me all messed up. So right here, we're going to write this from log to exponential. So we're going the other way around, from log to exponential. So to do this, we're going to start with the base. Our base here is 5. So we're going to get this base of 5, raise it to this power of 2, and that's going to equal to the value of x. So this right here in blue, 5 to the second power, is equivalent to writing that 2 equals to the log with base 5 of x. So let's look at this example, the next example. The next example, again, is a common log. Since the base is not written down here, that base is assumed to be 10. So we're going to zoom in and let's write this as 10. So since our base is 10, 10 will be raised to the third power, and that will equal to the value of the log, which this one doesn't have it written in parentheses. It doesn't have to, which is equals 1. Should be 1,000. Let's make a correction here. That should be 1,000, because I need this statement to be true. I need 10 to the third power to equal to 1,000. So this again is true. 10 to the third power equals to 1,000. Now for the last one, in order to write this one in its exponential form, remember ln, the natural log, has a base of e. So this has a base of e. So to write this into its exponential form, we're going to start with the base e. That's our base to our exponent. We're going to raise it to the power of y, and that equals to the value of x. So e to the y power equals x. And that's the equivalent form. Now remember, again, we are not changing the value of this thing. All we're doing is rewriting the equation into an equivalent form. That's all we're doing. So now let's work backwards. Let's convert the exponential equation into its equivalent log equation. So to convert this into a log equation, we start by first identifying the base. Our base is 12. So in this exponential equation, our base is 12, our exponent is 2, and it equals to x. So we start by writing the log of this base of 12. Okay, the value is going to be x, and it's going to equal to the exponent of 2. That's exactly what a log function does. The log function is just simply telling us the value that our base, our 2, again, our 12, has to be raised to the second power to equal to this number x. So this number technically should be 144. Since 12 to the second power equals to 144, then the log base 12 of 144 equals 2. Let's write the next one. Let's practice this next one. So to write this into its equivalent log function, again, our base is b. So this is going to be the log base b of the value 8. and the log with base b of 8 equals to the exponent of our exponential equation, which is 3. So this is the equivalent form for this. And finally, our last example. Here our base is e, so the log of base e of the value 9 equals to the exponent y. So this would be the equivalent form. Now, since our base is e, this is not the appropriate way of writing log base e with base e. The appropriate way of writing the log with base e is to write ln instead of log with base e. So we should write ln, the natural log of the number 9, and that will equal to y. So this is the appropriate way of writing this. And that's for, again, every situation when our base is e. If our, I'm going to do another one. If our base was 10, let's say this was instead 10 to the y power equals 9, then that would be log base 10 of 9 equals y. And when the base is 10, the appropriate way of writing it is just to write the log of 9. Because this right here refers that that number is going to be 10. So this is how you convert from exponential to log, and the top and this top part right here is how you convert from log to exponential. Now this right here is very important, okay? Sometimes we need to evaluate log expressions without using the calculator by utilizing again this equivalent form, by being able to rewrite this into this equivalent form. So let's practice that and let's see how we're going to use this. Okay. So we can use the idea that we can rewrite these things into its equivalent form in order to evaluate the logs without the use of a calculator. So let's look at example A. So for this example, to evaluate this, I'm looking for what does the log with base 2 of 16 equal, okay? So what we're doing here, if I look at the equivalent form, that means that this base of 2, that base of 2 is going to be raised to this unknown power, and it's going to equal to 16. So 2 to some power equals 16. So the idea is then, okay, how many times do I have to multiply 2 so it equals 16? That's what we're looking for. Well, 2 times 2, that's already equal to 4. So 2 to the second power is equal to 4. 2 to the third power will multiply just another 2, which is 8. And 2 to the fourth power will multiply again this answer here by another 2, which equals 16. So 2 to the fourth power, again, equals 16. So that's what we're looking for here. Our exponent has to be 4. So that means the equivalent value of the log with base 2 of this 16 equals to the answer of 4. And this again is what a log function does. It just tells us and identifies what the base has to be raised to in order to equal to that number right there. So 2 to the fourth power equals to this value of 16. For this example, well, this is again log with base 10. So let me write this as log with base 10 of 1,000. So what is this going to equal to? So again, what we're trying to do is to get this base of 10, raise it to some power so it equals to the value of 1,000. Well, 10 to the second power equals to 100. 10 to the third power will multiply 100 with another 10, which is 1,000. So that is our answer. Raising 10 to the third power equals to the value of 1,000. So this is our solution. All right. So let's look at the next example. So for this example right here, okay? So same situation. We're essentially looking at 7, the base of 7. We need to raise it to some power to equal to 1 over 49. Well, you should recognize that 7 to the second power equals to positive 49, but 49 over 1. Now, this is again where it's important again to recall all these exponent properties. Well, one of the exponent properties that we need to remember, very important, is our negative exponent property. That if x is raised to a negative exponent, then that is equal to getting the reciprocal of our base, 1 over x, and that makes the exponent into a positive value. Okay? So if 7 to the second power is equal to 49, then that would mean that 7 to the negative second power would be 1 over 49. So this exponent here has to be negative 2. So our answer is negative 2. Now this one's different because we're not getting a fraction, but what we're getting is 25 has to be raised to some power to equal to the value of 5. Well, this is another property that we reviewed when we were going over exponential expressions. We have the other option of having, again, a rational exponent. Now, we should be able to recognize and identify that 5 to the second power is equal to 25, but this is not what we're interested in. We're not interested in figuring out what power to raise 5 to get 25. We're interested in getting 25 to become 5. By using the fact that 5 to the second power is equal to 25, we can manipulate this. Because everything has an inverse, raising 5 to the second power would be the inverse to taking the square root to both sides. Okay? And as a result, the square and the square root cancel each other out. So that would mean, that would mean that 5 will equal to the square root of 25, which is true, right? Obviously, the square root of 25 is 5. Well, there's another property, again, another rational exponent property. Well, not another rational exponent property, but there's a property called the rational exponent property that we discussed in the beginning of this unit, again, on exponential equations, that if we are taking the square roots or the nth root, again, of any base, that is equal to raising that base to the rational value of 1 over n, to whatever that index is. And with square roots, that index is 2. So this would be x raised to the 1/2 power. So that means that 25, the square root of 25 can be written as 25 to the 1/2 power. So that is what our exponent has to be. 25 has to be raised to the 1/2 power in order for it to equal to this 5. So the log with base 25 of the value 5 equals to 1/2. Let's look at the last 4 examples. Well, this one looks very similar to the last one that we did, okay? we're looking at this. Again, 25 needs to be raised to some exponents in order for it to equal to 1 over 5. Well, we just found out, we just did the example that if I get 25 and I raise it to the 1/2 power, that equals to 5. Now that I want to get the reciprocal, I'm just going to simply apply both of these rules together. This rule here to get the 25 to become 5, okay? And then this rule over here in order to get the reciprocal of 5. So if 25 to the 1/2 is equal to 5, then that means that 25 to the negative 1/2, that's going to equal to 1 over 5. So that's what this base has to be. I'm sorry, this is what the exponent has to be. Our exponent has to be a negative 1 over 5 to make it equal to 1 over 5. I'm sorry, 1 over 2, 1 over 2. Let me start over. This exponent has to be negative 1 over 2. So 25 to the negative 1 over 2 equals to 1 over 5. That's what I meant to say. So let's write that. So the log with base 25 of the value 1 over 5 equals negative 1/2. So let's see this example right here. Here our base is 7. So 7 has to be raised to some power in order to equal it to the square root of 7. Well, this one should be easy to understand because we know that the square root of 7 is the same thing as raising 7 to the 1/2 power. That is not a y, to the 1/2 power. So in order for these two things to be equal to each other, this right here and this right here to be equal to each other, the exponents have to be the same. This is referred to as the one-to-one property of exponents. So let's write that down here, okay? The one-to-one property of exponents. So if b to the m power is equal to a same base to a different exponent power, then m and n must be equal. So this must be true. And this is what we're using, this idea right there. So this has to equal to 1/2. And then the last ones, okay? So here, 3 has to be raised to some power in order to equal it to 1. Well, this relies just simply on our 0 exponent property. That if our base is raised to the 0 power, that solution is always equal to 1. So regardless of what the base is, 3 to the 0, 4 to the 0, negative 1/2 to the 0, pi to the 0, that's all going to equal to 1. So the only way for 3 to equal to 1 is if 3 is being raised to the 0 power. So this right here is going to be 0. And for the last example, well, the log base 7 of 1, what is that going to equal? Well, that means again that 7 has to be raised to some power, so it becomes 1. Well, this again, the exact same situation as before. The only way that this becomes 1 is if 7 is raised to the 0 power. So this is also going to be 0 as well. Okay. All right. So this is how we evaluate logs using, again, the idea that we can convert a log into an equivalent exponential form. Now, let's study again these last two, H and G, a little bit closer. Now, the last examples follow a basic property involving 1. That if we're taking the log with base b with the value of b, as you see right here in this first one, let me zoom in on this one right here, then the solution is always going to equal to 1 because b to the first power has to equal to b. So when these numbers are the same, the value is going to be 1. And on the last example, as we just discussed, again, the log of any base of the value 1 is always equal to 0, because the only way to get this base to equal to this 1 is if the base is raised to the 0 power. Okay, so let's use these two properties to evaluate the following 4 things. So right here, the log base 7 of 7, that's going to equal to 1, because 7 to the first power equals 7. 7 to the first power equals to that 7. So the log base 7 of 7 equals 1. And the same thing with natural logs. Remember, ln is the same thing as log with base e. And since these two bases are the same, the base again is equal to the value of the log, then that means again that this should equal to 1, because e to the first power equals e. So that's our solution. Now let's look at the second basic property, again involving 1. If we're looking at the log of any base of the value 1. So here, the natural log is log with base e of 1. Well, how can we get e to equal to 1? Well, our exponent would have to be 0. Our base e would have to be raised to the 0 power in order for it to equal to 1. So the natural log of 1 equals 0. And the same thing with any other base, regardless of what the base is, whether it's 8 or e. If we want the log with base of 1, that has to mean that this has to equal to 0, because 8 to the 0 power equals 1. Now there's two other properties that are very important, the inverse properties of logs. Like for any base greater than 0 not equal to 1, then the following are going to be true. The log with base b of b raised to a power equals to that power, as indicated right here, okay? So this right here. So the log of base b of b to some exponent is going to equal just to the exponent. And essentially these two things just cancel each other out, in other words. And the same thing if it's the other way around. If I get b and I raise it to a log with the base of the number equals, again, just whatever that number is. So if this base and this base are the same, these two things cancel each other out, and they're going to equal to that value right there, to that x right there. So like in this situation, notice the base of the log and the base of this exponential expression are both the same, 4 and 4. So that means that these are going to cancel each other out, and this is going to equal to 5. The same thing right here. Remember that this has a base of e. So these two things are going to cancel each other out, and the only thing we're going to be left with is x. And this again is the second one, the second inverse one. Since the base are the same, those two things cancel each other out, and the only thing we're going to be left with is 9. And the same thing here, this has a base of e, so these two things cancel each other out, and all we're going to be left with here is x to the second power. Okay, moving on to the next page. Now, one useful purpose for logs is when dealing with exponential data. Exponential data can be very challenging to display graphically because the values may start over very small and but then they grow very quickly. Now, it's difficult to create a display that effectively shows the smaller values along with the extremely large values together. For example, look at this graph, these two graphs that we have here on top. This right here represents the population of the English Americans in the current United States from 1620 to 1820. And it's growing exponentially, as you see here in this graph right there. It's growing exponentially. The estimated population, again, when t is equal to 0, represents the year 1620. Now you'll notice that the graph on the left shows the population using a normal scale on the vertical axis, okay? 1 million, 2 million, 3 million, and so on. Now, because the population expanded into the millions, the data points represented in the years 1620 to 1700, which again is our first 80 years, right, are almost indistinguishable. You cannot tell again what those values are right here. It would be difficult to notice any difference in the population during those beginning years. However, the graph on the right uses a log scale base 10 for the vertical axis, as you see right here. So 10 to the first power, that's 100. 10 to the second is, 10 to the first is 10, 100, 1,000, 10,000, 100,000. 10 to the 6 is a million. Again, a 1 with 6 zeros, and so on, okay? Using a logarithmic scale allows us to view all of the data, as you see right here, all of the data relative to each other. So again, this is one of the useful purposes of using logs and converting between an exponential to a log base equivalent form. Now, let's use this idea in order to plot some points. So let's, for example, look. The population of English America in the current United States from the years 1840 to 1860 and 1890 are given below. Let's plot these 3 additional points on the graph above. So here, we can plot these points at 1880, which is going to be 220 years from 1840, minus 1620. That's a total of 220 years. So in 220 years, we're going to be at 17 million. So that's above right here. This is a million. Okay. There, 1 million. 10 to the 6th power means a million, 6 zeros. So 17 million is going to be obviously somewhere really close to that. Okay. 31 million will be a little bit higher than that, and 50 million will be exactly in the middle. So somewhere right there. Okay. So this is what the plot will look like. It will not go above this vertical line right here, because 10 to the 7th power, that is 10 million. So it would have to be below that. Now, one common type of graph with a logarithmically scaled vertical axis includes grid line that's shown below. Now, this is a type of coordinate grid that's likely going to appear on your AP pre-calculus exam. So this one right here, okay? So let's use this and let's understand this and learn how to plot points following the same coordinate plane above. Now, while I have it already in base 10 and they're already written in values, it could also be written like this, where instead of 1,000 or 110 or 1, it's written as 10 to the 0 power, 10 to the first power, 10 to the second, and 10 to the third, instead of those numbers there, okay? So let's start by plotting point A. Well, point A has an x coordinate. Again, this is your x, this is going to be your y coordinate, an x coordinate of 120. So when x is equal to 1, which is right here, okay, the y value has to be 20. So if this is 10, again, these are going in increments and scales of 10. 20 would be right here. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100 when I zoom in. So 120. So like I was saying, 120 would be right here. So that would be A. To plot 300, well, again, 2 for x is obviously this right there. And 200 would have to be, again, above 10 to the second power. Since this is 100, this would be 200, and this would be 300 right there. So this is point B. For point C, that would be 3, 2, so 3 for x. And since this is 10 to the 0 power or 1, this is 10 to the 0 power or 1. This is 3, 1, 3, 2. So this point right there would be 3, 2. C. 415 would be, again, not 5 higher, because, again, these are going in increments of 10. This is 410, 420, 430, 450. So 415 would have to be between 10 and 20, so somewhere right there. So this would be D, and the last one, 5 and 350. Well, 5 and 300, this is 100, this is 5 and 300, 100, 10 to the second power. This would be 5 and 200, and then this point right here would be 5, 300. So 350 would be in the middle. So right here in the middle between 300 and 400. So that would be right there. And that would be letter E. So these are the coordinate points for this using this logarithmically scaled vertical axis. Okay. All right. Well, that concludes again the notes on log functions. If you have any questions, please send me a message through email. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.